All right, so the three rules we're focusing on today, just real quickly in review, the sum difference rules are really, really easy. We've been talking about single terms when we talk about the power rule, and now we're going to be talking about polynomials that have multiple terms added or subtracted together. So the easy thing about this is if you have multiple terms, you can actually view them as different functions. And if you have multiple functions that are added or subtracted together, and you want to take the derivative of that expression, you simply take the derivatives of each individual term, and you either add or subtract them, and we'll do lots of examples. The constant multiple rule, this is a rule we don't really use that much, and we're going to combine the power rule and the constant multiple rule just to make it easier. But with the constant multiple rule, you'll see this in your book, and what it says is that if you have a constant that is multiplied in front of a function, when you take the derivative, it's just like removing the constant out in front of the derivative and multiplying by the derivative. Now, if you remember with the limits, remember limits in chapter 1, one of the limit rules was the constant rule. And if you took the limit of a function, but it was multiplied by a constant, you could take that c constant and bring it in front of the limit, remember? And just take the limit of the variable expression. And then when you found that limit, you multiplied at the end by the constant. So in limits and in derivatives, we can literally pull the constant that's multiplied by everything. We can pull that out and deal with it later. Okay? Now, are we going to do that? Again, I would say that we're going to combine the constant multiple rule and the power rule, and it's going to be much easier, but I'm just showing you what technically the constant multiple rule is. So if we had, for example, here's just a quick example. If the function, okay, was 3x squared, and I want to take the derivative of this, and in our activity yesterday, what we noticed is we multiplied 2 times 3 to get the new coefficient. Now, that's a combination of the power and the constant multiple rule. Technically, what they would say would be this. They would say the derivative of this whole function could be viewed as 3 times the derivative of x squared, or write it like this, x squared, the derivative of. Okay, what does that mean? Well, all that means is that you leave the 3 out front, and then you write this as 2x, and then you simplify. So you see how we get the 3 times 2 anyways? And so we're just going to combine those two rules into one, and we're always going to multiply the exponent by the coefficient. And so this would be 6x. So I don't want to confuse you, but when you see a constant multiple rule, like, oh, Mr. Maxwell didn't teach us that. Well, we are combining some of these separate rules, just like we did with limits, okay? So let's do some examples, and here we go. We've got f of x equals 2x to the 4th plus the square root of x. So let's focus on a here first. So the sum rule says that I can take this first term and this second term separately, and I can find the derivatives of each. So I'm going to write this out just so you can fully see what I'm doing. And I'm going to also change this square root x into an x to the 1/2. Because remember, we're kind of focusing on exponents when we take derivatives of terms. So I'm going to rewrite that as x to the 1/2, and you're probably going to want to view square roots as power of 1/2, cube roots as to the power of 1/3, fourth roots as the power of 1/4, and so on. So again, in taking this, going to combine the constant multiple rule and the power rule, and we're going to do this right here. 4, bring that down and multiply this by 2 to give us 8. X, retain your variable there, and then I'm going to subtract 1 from 4. This is going to be x cubed. So the derivative of 2x to the 4th is 8x cubed. And because that's not the only part of the expression, we're going to add, because that's what I have here, and I'm going to take the derivative of this part now. And so when I take a look at this, we just have a variable to an exponent. I'm going to bring that exponent down in front and as a constant multiplier there, or as a coefficient. And I am going to subtract 1 from 1/2. So 1/2 minus 1 is the same as 1/2 minus 2 over 2, which is negative 1/2. Very good. Negative 1/2. All right. So that's the differentiation part, and we're done. except for at this point, you're probably going to want to, and the textbook will urge you to, and just for simplicity's sake, let's get rid of negative exponents. Let's simplify those and bring those down to the denominator. And then usually a half is written as a root, especially if it's a root in a question. You'll kind of want to retain that sort of notation for the answer. So f prime of x is going to be 8x cubed. And this is going to be, this is a x to the positive 1/2 in the denominator, which is a root x. So I'm going to do a couple things at once. Watch carefully. The 1 stays up there. I have a 2 in the denominator, and I now have a root x in the denominator. Okay? So 2 things at once. I brought this whole thing down to the denominator, and then I rewrote the positive 1/2 to a square root. And this would be your answer here. All right, let me know, class, if you have any questions about that. Going once, going twice. Yes?
Is it okay to just delete the radical of the denominator?
Yes, it is okay to leave the radical in the denominator. Thank you for asking that. In pre-calculus, you're right, I've kind of been preaching to you for years that generally simplifying you wouldn't leave a radical in the denominator. You would simplify that to put the radical in the numerator. That's not the case in calculus. It's not necessary. Just typical convention. You'll see this all the time. Yeah, very good question. You do not have to rationalize the denominator like we did in previous classes. True. Thank you for noting that. Yeah. Great. Any other questions? Yes? Where did the negative go? Okay. So in exponent rules, what you would remember is, let's just use a number. So 5 to the power of negative 2. If you plug that into your calculator, actually let's do 2 to the power of negative 2. If you plug this into your calculator, you get 0.25. Okay. Now, how do we make sense of that? Well, we make sense of that by using one of the exponent rules, which says that if you have a negative exponent, whatever the negative exponent is applied to, this whole package would be, if you made it the reciprocal, so if it was in the numerator, you put it in the denominator, and then it would become positive. So that's actually 1/2 to the positive 2 as an exponent, which is 1/4, or 0.25, okay? So anything with a negative exponent, whatever that exponent is actually attached to, that's going to come down into the denominator to become positive. So that's just an exponent law. Okay? Okay, good. Any other questions? Let's do B. Let's do B then. So okay, so here it is. G of x is 6x to the 4th minus 5x cubed minus 2x plus 17. All right, so what we understand using the sum and difference rule is that if I wanted to actually find the derivative of the function g of x, and don't worry about the g, what's with g, f, h, what's going on, it's just noting different functions. So it could be g of x, it could be h of x, it could be w of x, whatever. It's no big deal. But this is the derivative. So what I want to view this as is I want to take the derivative of each of these terms separately, and then just, retain the minus or the plus in between them, and then simplify after that. So what's the derivative of 6x to the 4th? 24x to the 3rd is correct. And we get that by multiplying 6 times 4 is 24. I write the x down there, and the 4 is subtracted by 1 to get 3. Perfect. Minus. Okay, difference rule. And now I focus on this one as the second one. So what's the derivative of 5x cubed, everyone? Go ahead and shout it out.
15x squared.
15x squared is absolutely correct. 3 times 5 is 15. X to the power of 3 minus 1 is 2. Minus, what's the derivative of 2x now? Careful.
2.
Just 2. That's right. Now, why is that? If you're wondering, you're going to memorize this. This is going to be this is just going to be memory. But 1 times 2 is 2. And then times x to the power of 0. X to the power of 0 is just 1. So that's why that just becomes 2. Okay? Plus, what's the derivative of 17?
0.
It is 0, and as we spoke yesterday, you can view this as, watch this. This is 17x to the power of 0. And so the power rule does apply to this as well. 0 times 17 is 0. X to the negative 1. Well, that's just 0. 0 times anything is 0, so that's just 0. Okay? Now you won't have to write the 0, so we will just drop that now, and this is our final answer. I'll highlight that in yellow. Final answer. Okay? Questions on that? No questions on that? No? None? Going once, twice, 3 times? No? Okay. Good. You guys are so smart, that's why. Okay, great. Okay, let's differentiate the following functions, and I'm going to let you do this on your own. See how you do with it, okay? So go ahead and please differentiate the following functions. You may get a little stuck on some of the ones that you haven't seen yet before, but I want to see if you can figure out what to do, okay? i.e. the second and third one. I don't think the fourth one should be much of a problem, but the second and third one. If you need to confer with a classmate beside you, please go ahead and do that. But try and do what you can here, and I will show you the answers in a bit. Okay? All right, so let's take a look at what we got here so far. So the first one, pretty straightforward. It's 3 times 5 is 15x to the power of 5 minus 1, or 4, minus 24x cubed, and then plus 0. So that's the answer for the first one. The second one is going to be, what we're going to want to do is view this term right here as a regular old term with a negative exponent. So you can use the power rule. Okay? So I rewrote that. And then take the derivative. Okay? Again, the sum difference rule, you can probably do this negative times a negative in one step. I'm totally fine with that. You're going to get that. But just so you can see what's going on here, I took the derivative of this separately, and then the negative times the negative there is addition. I also wrote the negative exponent as a positive exponent in the denominator. So there's your second one. Questions about that? About number 2? All right. The third one. So this one maybe caught you off guard a little bit, but what you're going to want to do is at this point, there are going to be more rules as we move through that you're not going to have to expand multiplications of binomials, but at this point, you need to expand because you only know a certain number of rules. So you need to get the polynomial form. So you're going to want to do your FOIL method, multiply out here. Let me zoom in a bit. So you guys know how to do this, obviously. X times x is x squared, plus 6x minus x minus 6. Combine those like terms. Now take the derivative of each individual term, and you get 2x plus 5 for that one. Anybody get that? Okay. And finally, the last one with this negative, again, you take the individual derivatives there and combine them. Now they did have a negative in the question, so you'd be probably okay to leave that negative 6 as an exponent, but generally this is a good habit to get into. So that's the way I would write that. Does that agree with what you guys got for those questions? Yeah? Okay. Oops. I was going to zoom out a little bit there. Okay. All right. Excellent. Hey, if you can do that, that's really, really positive. I'm really happy about that. All right. The next little concept that I want to talk about here in this section is determining equations of tangent lines. So we've done this before, right? What we have to do is we have to find the slope of the tangent line and use the point of tangency to build a linear equation for the tangent line. So we're going to do the same thing that we did in chapter 1, except now we're going to have some rules that will simplify how to find that derivative. Okay? So find the equations of. Now this one's a bit tricky because there are 2 possible solutions. There are 2 lines that pass through this point on the parabola that's given here that are tangent to the parabola and that pass through this point. So we're going to sketch the parabola and the tangents. Okay, so this one is a bit of a bit more of a complex question because there are 2 lines that we have to find. So go ahead and just jot that down. Okay, so as I mentioned, this is a bit of a complex question. A good question for you to see and to understand. Now, it says sketch the parabola and the tangents. It might be a good idea to have in your mind what the situation looks like. This point right here, 2, 9, is not on this parabola. okay? Because I know because 2 times 2 is 4 minus 4 is 0, not 9. So this is not on the parabola. So what's happening here is we have a parabola that opens downward, okay? Has a and it has a y-intercept of 0 because there's no constant, okay? So just roughly it looks like this, okay? Now, you could run some points if you want, but this is kind of what it looks like. The point 29 is up here somewhere. This is 29, okay? All right. Again, if you did a table of values, you could run some more points and see what's going on there. Now, what we're looking for is the equation of the two lines that would be tangent to the parabola here and here. Okay? So this is a little tricky. It's a little tricky. What we have to understand is how does the derivative play a part here? What is the formula for slope? How do I include a point or 2 points in the slope formula? Put it all together. So again, this is the one that I'll walk you through. So I know that the slope of the tangent will be the derivative of our function. Okay, so that's the expression for the slope of the tangent. We don't have a point of tangency here yet, so that we can't use an x value to find an actual slope of the tangent lines because we aren't given this point and this point, whatever it is, right? We're not given those points. So what we have to do is we have to kind of piece this together, and from what you know, the formulas you know, what the derivative is, how to calculate slope, we kind of have to put this puzzle together. So y prime is going to be what? 2 minus what? Minus 2x. Are you good with that? 2 minus 2x? That's the expression of the slope of the tangent. Okay, this is the expression. And so from our diagram, what we see is the slope of the tangent plays a part in that the slope between this point and some random point on the function is going to have to equal, this expression. Or if I let the slope equal sort of a definition of a slope or a calculation of the slope, then I can find a missing value. So let's find, let's say that we're going to let, so A is going to be the x value for point of tangency, okay? So instead of all x's, we're going to do a's here for point of tangency. And this is unknown. These points are unknown. So I've got unknown x and y, or a and f of a. Okay? That's what I have. That's an unknown point a and f of a. And so if I have the expression for the slope of 2 minus 2a, and I'm going to make this a different color because 2 minus 2a, that's what the slope has to equal. And how do I get the slope? I get the slope from doing y2 minus y1, again, a is unknown, divided by x2 minus x1. Okay? So I'll just write that right here, y2 minus y1 over x2 minus x1. And I'm going to now fill in those values because I'm going to make an equation that just includes a. So the slope here is 2 minus 2a, and y2 is 9. y1 is f of a, which is actually 2a minus a squared. How are you feeling about that? 9 minus 2a minus a squared. That's what f of a is. Divided by 2 minus a. And if you, doesn't matter what point is x1 and x2, actually. It doesn't really matter. But now what we're going to try and do is we're going to try to solve for a, because I have now an expression, so what my slope equals, and then how you would determine the slope. And it's only got one variable in it, which is great. So I need to try and solve for a now. Does everybody understand? If I can solve for a, that means I can find out what point or points, and we know there's going to be two, what point or points will be allowed here. So let's do some simplification here. So I'll leave that side alone for now. This is going to be 9 minus 2a plus a squared all over 2 minus a. Okay, might be a good idea to get rid of the denominator over here, right? And so we can gather some like terms. I don't want a denominator, so let's multiply everything by 2 minus a. So 2 minus a times 2 minus 2a. What does that give us? That gives us 4 minus 4a minus 2a plus 2a squared, or 2a squared minus 6a plus 4. That's what's on the left side. And on the right side, of course, is just this right here. So I've got 2a squared minus 6a plus 4 on the left. And I've got, and I'm going to rewrite it just in reverse order here, a squared minus 2a plus 9 on the left. Or on the right, sorry. So you can kind of see, all right, I can gather some like terms. This is going to be a quadratic, right? So I'm going to put everything over to the left side, let it equal 0, because then I can use the quadratic formula, or I can factor, maybe, and use the zero product principle. So if I get everything over to the left side, subtract a squared, add 2a minus 9, I'm going to get a squared minus 4a minus 5 equals 0. And I can factor this by sight, I think, pretty easily, right? We can factor this by sight. So this is going to be a is going to be our first term. I need to multiply to 5, negative 5, add to negative 4. So that looks like it's going to be minus 5 plus 1. That multiplies to negative 5 and adds to negative 4, right? So what are our solutions? A would equal positive 5 and negative 1. Positive 5 and negative 1, okay. So what that means is that in order for all of this to be true, what we set up here, in order for all of this to be true, to be consistent left and right side, then I could use a equaling 5, should work, make the left side equal the right side, and I could be able to use a equals negative 1 in there, and the left side should be equal to the right side. And so those are the two solutions for the x values of a. Okay? So, if a equals, let me make myself a little more room here. If a equals negative 1, what do we get? I'm going to speed this up just a little bit. If a is negative 1, then f of a is going to be negative 3. If a is positive 5, then f of a is going to be negative 15. So we have 2 points. That is negative 1, negative 3, and negative 5, sorry, positive 5, 15, negative 15. Okay? And if you look back up at the graph, if I can get that all on one screen for you, if you look back up at the graph here, this point looks pretty close to being negative 1, negative 3, and this point looks pretty close to being positive 5, negative 15. So in our little sketch here, these answers would be perfectly reasonable. And now what you could do is you could use the a value, right? And you could find the slope. What is the slope of that tangent line at negative 1? Well, it's 2 minus 2 times negative 1, or 2 plus 2 is 4. So this would be a slope of 4 right here. And then at positive 5, 2 minus 10 is negative 8. So this slope is negative 8. All that lines up. Okay? All right. That's a top shelf, high level question, isn't it? Okay? That's a bit tricky. But this is the sort of thinking that I want you to think about. Okay. Got to keep moving. Got to keep moving. I want to talk to you about domain of derivative and functions, because that's come up in your it's come up in your assignments, and I don't know if you guys have asked me about that yet, but remember the key points in determining domain. That is all possible values for x, the domain. So we can't be dividing by 0, that's bad, and we can't have a negative under a square root or a radical with an even root, 2, 4, 6, that sort of thing. So we can't have negatives under there. So that's what we're looking for. So let's find f prime and state the domains of both the original function and the derivative. So for a, f prime of x is derivative of 1 is 0 plus, what's the derivative of x? What's the derivative of x? 1. I heard 1 a couple times. You guys agree with 1? Okay. So remember, any x term, the derivative is always its coefficient. If it's just x to the 1, the derivative is the coefficient. So yeah, this is just derivative of x is 1. Very good. This one here is going to be 2 times a half, which is 1. X to the power of 1. So the derivative of 1/2 x squared is x. Whew, that's weird, isn't it? Okay, what's the derivative of 1/3 x cubed? 1 times x to the 2, or x squared. 1/4 x to the 4th, well, 4 times a quarter is 1 x to the 3. It's just x cubed. So here's the derivative. We'll get rid of that 0. There's the derivative of this function. Okay? Domain of f of x. Okay? That's going to be x is all real numbers. It's just a straight polynomial. There's no restrictions. X is not in the denominator. We don't have to worry about it being 0. X is not under a radical sign. We don't have a fractional exponent here, so I don't have to worry about that. So it's just XER. What about the derivative? Take a look at this. Is this just a straight polynomial as well? Any restrictions that you see there? That's going to be XER too. Okay. Now we might run into a bit of an issue with B, because I see already that I have a radical. Okay, let's see, what? Okay, here we go. I'm just going to pull this down here. So I do have a radical there, so that might cause a bit of a problem. What's our derivative? What's the derivative of 4x? 4. Good. Now you might want to rewrite this. I mean, you don't have to. If you can envision it, you don't have to rewrite it. But keep in mind that that's x to the power of 1/4 if this index is a 4, right? Okay. So what have I got here for a derivative? I'm going to have minus what? 1/4 x to the 1/4 minus 1. What's that? So don't get too stressed out about this. Just make it a common denominator. So 1 is 4 over 4, right? So that's negative 3/4. Negative 3/4. Okay. So you might also remember that if you have a fractional exponent, okay, the bottom number of that fraction, the denominator, is the index of the root, and the top number is what would be the exponent on the variable. So putting all this together, that's going to be 1 over 4 times the 4th root, the 4 goes in the notch there, of x cubed. And the cubed can go inside or outside of the radical. It doesn't matter. They're both the same. Okay. Okay. So so now we look and we say, okay, domain here. Okay, what about the domain for the function, f of x? Well, do we have issues with x here? Are there any x values that this cannot be? Cannot be what?
Less than 0.
Yeah, it can't be negative, right? So x is fine over here, but not fine here. X has to be greater than or equal to 0. So the domain here is x greater than or equal to 0. Now we have to look carefully at this one. We also have an even root, so this can't be negative inside here. X cubed, does this cubed make everything that x is become positive? Like a squared? Or no, it doesn't. So we still have issues under here. So x cubed can't be negative. Therefore, x cannot be what? So the domain here for f prime is it the same, or what are your guesses, thoughts? Okay, x has to be greater than or equal to 0. What about equal? Yeah, why not equal?
Because if x equals 0, then the bottom.
Ah, yes, thank you very much. So for this alone, x is greater than or equal to 0. That would have to be, but because this is in the denominator, red flags. So this cannot be 0 in the denominator, therefore x cannot be 0, so yeah, it has to be greater than 0. Any questions about that now then? Are your solutions? Okay, finally, the last part of this lesson here, find x values that have a given derivative. So this is, again, these last couple questions are part of your assignment, so I'm just kind of helping you with your assignment here. So go ahead and jot that down. Okay, as you finish jotting that down here, let me just give this a start for you. So at what points does the curve, this graph, have a horizontal tangent? So I don't know, it's a cube function, so it could be, you know, something like this or whatever. Actually, it's going to be the other way. It doesn't matter what it is, but there's going to be possibly, you know, two points on the graph where we could have a horizontal tangent. So we have to try and figure out what those are. And how do we do that is we know that a horizontal tangent, the slope of the tangent would have to be equal to 0. So what you're going to do is you're going to find y prime here. So find y prime and let equal to 0. And then solve for x. Those are your steps. So y prime is, what's the derivative of 3x cubed? 3x squared, good, plus 6x, good, minus 24, and then plus 0. Awesome. So found y prime, awesome. Let that equal to 0. So I'm going to put 0 on this side, and now it becomes a quadratic that I can just solve for 0. Now I do have, to simplify this, it looks like I have a common factor of 3 here. Does that make sense to you guys? So I'm going to divide both sides by 3 to get rid of that. And that's going to turn into x squared plus 2x minus 12.
24 divided by 3.
Oh, sorry. I was dividing by 2. You're right. 8. Thank you. X squared plus 2x minus 8. Perfect. So now we are going to factor this. It's going to be x as the first term. What are the two numbers that multiply to negative 8 and add to 2? Plus 4 and minus 2. Does that look good? All right. So that's actually what the graph looks like there. So that means that at x equals negative 4 and x equals positive 2 should be the solutions to this question here. So at what points? So if the question asks for points, just a heads up, it's not good enough to just give x values, you have to give the y values too. So if x is negative 4, you'd have to put negative 4 in for x wherever you see it in the original function to get your values there. And so the points are going to be x values of negative 4 and positive 2. So the points will be negative 481 and 2, negative 27. So our graph would roughly look like this, not exactly to scale, but here's our negative 481 point, and here's our negative 2, sorry, positive 2, 27 point. Positive 2 and negative 27. All right. Okay, okay, that's that question. Now, I did kind of lie before. There is one more thing I wanted to show you before I let you go. So we have time for one more little thing. So any questions about number 7? All right. Okay. Another section, another question in your assignment here. Differentiability and piecewise functions. Okay, so number 12. And again, I'll get a start on this. We'll see how far we get with the class time we have. But just a reminder, when we talked the other day about differentiability, okay, and you jotted this down in your notes, that a continuous function, most continuous functions are differentiable everywhere on their domain. There are a few exceptions, right? So for example, non-continuous, obviously, if we have a jump, right, a jump discontinuity, it's not differentiable here at this x value. If we have a corner or a cusp, so if we're talking about, you know, like an absolute value function or something like that, where we have a corner, straight line, and then another straight line with a different slope, it's not differentiable there. Cusps look like this, where you have a graph that kind of like is concave up and then concave up again, but kind of looks like that. That is not differentiable. And again, I don't have the time right now to go into that, but there are certain parts or places in the domain of a graph where it's not differentiable. And so we touched on that a little bit yesterday. So this one is asking you, where is f differentiable? What you're going to look for is continuity, okay? You're going to look for continuity is the first thing. And then if you have like a square root, or if you have a absolute value or something like that, that may yield some sort of corner or cusp, that kind of thing, yeah, then you're going to have a problem. So, where is f differentiable? It's asking for which values of x would be differentiable. So there would be only a few values of x, or 1 or 2 or 3, that wouldn't be differentiable. So it's asking you sort of to locate where this might not be. And quickly, for continuity, we could check this. So where x is less than -1, that's kind of on the left side of the graph there. We have a straight line. And at -1, what would the value of this be? This would be -2 plus 3 is +1. So at -1, this value would be +1. And what would the value be of this one at -1? Well, that would be +1 as well, -1 squared. So it appears that these do meet at the same spot. It appears that it's continuous there. Now, we have definitely different types of graphs. So the question is, we have a straight line, and then we have an x squared. So we have this. Does that look like a corner or a cusp, or something that is not nice and evenly flowing in the same curvature? It does, doesn't it? It's continuous, but that does not look like it's a continuously flowing part of a graph. That's a straight line, boom, and then all of a sudden you have a curve. So that looks like that would be a corner. So different types of graphs meeting like that might cause an issue. So let's talk about continuity for the next one at +1. So obviously at +1, x squared is 1. At +1 here, 3 minus 2 is 1. So it looks to be continuous, but here we jump into another straight line, so it's quite abrupt here, where we have another looking like corner. So this is not differentiable at -1 and +1 because of the abrupt changes there, okay? And yeah, gonna have to say this for next lesson, but sketching graphs of derivatives, we'll take a look at that in the next lesson. And there's your assignment. Okay, you guys are dismissed.